Hello folks, welcome back. So after class on Wednesday, I had all the best intentions of getting your quizzes graded and your homework 0 uploaded, and then Huey got sick and was out of daycare for the last 2 days. So I'm a little behind. Hopefully I will get that stuff done later today. He's feeling better, of course. Kids are resilient like that. I hear everyone's sick though. Is this a thing right now? Everyone you know is sick? Except you guys? You doing okay? Well enough anyway? Good, good. I'm still well somehow. I'm not sure how that happened, but I am. And I've also been answering emails about your attempts on homework 1, so I thought I'd start there and see if there's any of these that folks wanted to talk about. One thing I've already answered 2 questions on. The instructions specify maximum likelihood this time, so make sure that you have that specified in your code correctly. Otherwise, you'll note the usual suspects in terms of things to troubleshoot. If you don't have the right model, -2 log likelihood, you don't have the right model. So don't try to go further until that's correct, and it should be correct to 3 decimal places. If you don't have the right fixed intercept, then you don't have the right centering for your predictors. So that's your check there. You can have the right things in your model and not have them centered appropriately, still get the right -2 log likelihood, but that will result in an incorrect intercept. From there, you'll note a suspicious similarity in the questions in each section. They're the same. The idea is for you to look at these fixed effects that the model predicts and then to realize how the model predicts them differently after you add the new interaction terms. So don't think too hard on some of these earlier questions because some of them are easier than you think. So for instance, predict the quadratic slope ... In this first model, nothing interacts with time or time squared. So when I say predict the quadratic slope, do you need to even keep reading? It's the same for everybody if it doesn't interact with something. So predict the ... for, make sure that that term is actually part of your model as a modifier of the effect. If not, it's just whatever the fixed effect says. So any questions on this right now? It's due Friday, so you still have a while yet. Yes? Just getting the model to be right at all. Okay. So random quadratic model is what we're looking at. Time 0 should be occasion 4. And when I say random quadratic, that means the model line must have linear and quadratic time, both centered at 4. And the random line must have intercept, linear time, and quadratic time, all centered at 4. Then in which the intercept is predicted by sex, education, and their interaction. That's code for what? What type of effects predict the intercept? It's better to be wrong than vague. Yell it out. What? Yeah. What kind of effects predict the intercept specifically? Starts with an M. Main, yeah. 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 The intercept is the conditional outcome. So when I just say what predicts the intercept, those are main effects. The intercept is predicted by sex, education, and their interaction. So sex by education is a level 2 interaction, but it predicts the intercept. But the linear and quadratic time slopes are unconditional. That's code for marginal. That's code for doesn't interact with anything yet. From there, you'll be adding interaction terms, where moderation means interaction term. Does that help? Okay. Do your sex and education predictors go on the random line at any point in this? No, they do not. Will SAS run if you put them there? Perhaps. But in this example, those are time invariant level 2 predictors which cannot have random effects in a level 2 model. They could if this were a 3-level model, but we are not there yet. All right, any other questions? Jacinta, are you waving at me?
Yeah.
Yeah, okay.
I was just writing something. I was wondering with this work, I'm still finishing up going over the last semesters, and I'm wondering if it falls in between homework 7 and 8.
Yes, I would say it's past 8 even in terms of complexity.
Okay.
But it's 7-ish in the sense that you're looking at instantaneous linear slopes at particular times.
Okay.
So yes, this is moving forward. So it's review and extension.
Okay.
Yeah, more practice with the same concepts though. Sure. Any other questions? Okay, then I will close this for now and pick up where we left off with story time, which we were also practicing estimate statements. So it is challenging initially and still challenging to some extent even after practice to listen to someone's description of their data and their questions and try to figure out what the model needs to look like to actually answer the questions. But this is a really important skill. This is a skill that you will need to develop for grant proposals, for any kind of research product, really. You have to have a plan as to how you're going to actually answer the questions. And it's good to think about the plan before you even collect the data, because the way you collect the data may change as a function of the plan. So the first 2 examples that we looked at last time were what I would call continuous time examples. They were observational studies. Nothing happened on the part of the research team other than calling these people in every so often and measuring them on whatever outcomes. And in each of these cases, it was a time invariant predictor, something that was measured once that you were looking at as a moderator of intercept and change. So we looked at this one here, which was a quadratic model that had letter ID as a predictor. So it ended up looking like that. And then we looked at this one, which was a linear model, which had 2 predictors of tobacco exposure and gender and their interaction in predicting the intercepts and linear slopes. And we talked about how to get simple slopes for each of those types of groups. Any of that you want to go back over or hear again? No, those are good? Those are good? Okay. So the final product here of what she found looks like these lines, by the way, where you can see which slopes appear to be different, and that's what the estimate statements would allow you to confirm which of these slopes are different, which of these intercepts are different, and so forth. So then we switch gears to the 3rd example. And the 3rd and 4th here, I specifically picked because they go against one's initial inclination in longitudinal models. So you will get this if you go to, say, a workshop on longitudinal models that lasts like a day, for instance. They will show you how to model fixed and random effects of linear time and then you're good to go. Now you can do longitudinal. Or if you take an SEM course that has a week on longitudinal, odds are good. You will get to your random linear slope model and you know longitudinal, right? You're done. It's that easy. It's not that easy. So these last 2 examples are specifically when that approach is not going to answer the questions. And it doesn't even make sense given the way the data were collected. So this is a study on number 3 that I helped several different graduate students with at UNL. I don't have enough information to give you specific authors or publications, but I can give you the story. It was measuring treatment effects in people who have severe mental illness. And so these are, it's a clinical population, an actual hospital, so they don't have a whole lot of control over everything. But the design of the study looks like this. When you're treating people in a hospital, it's sort of unethical to have a control group, right? You can't withhold treatment. That's maybe not the best idea ever, even if it's the strongest experimentally. So what they ended up doing was this idea of a wait list control. It's like, no, we're going to treat everybody, just we'll treat some of you first and some of you second. That way we have something that looks like a control group. And they only had 3 occasions: before treatment, after treatment, and then some kind of follow-up in the distance. I don't remember how far apart these are, but they kind of don't matter because there's only 3 occasions. So the green line here is what it would look like for the people who got treated first. They have their before measurement. Hopefully they get better after treatment is over, and ideally they would maintain their improvement through follow-up. The people who didn't get treated yet, they got treated after the second occasion. They would continue their level of severity as per usual. Something would happen and they would get better by the time wave 3 happens. And this design doesn't allow us to indicate whether or not they would maintain that treatment. We would need another occasion. So this is the idealized way the data would look if the treatment worked for both groups and the green group got to maintain it. So if I attacked this type of design with my random linear model, would that make any kind of sense? No, what does linear mean? Let's back this down. What kind of change pattern does linear imply? Straight line, constant. The same amount of change per difference in time. But difference in time in this study is code for difference in procedure. There is no reason that there would be the same amount of change from any of these occasions in any of these groups. 1 to 2 to 3 should look different for purposeful reasons in each group. And it should look differently different depending on which group you're in. So this is an instance in which the so-called right model is easy to pick because I would just go with the most complex model you can have for 3 occasions. So I've written out the equation to be consistent with how we would talk about it for the other ones, although if I were writing up this paper, I probably wouldn't bother with an equation. But this equation doesn't have any residual terms in it. It's the model for the means only, because what I would do for 3 occasions for the model for the variance is just let it be unstructured. 3 occasions, that's not a whole lot of parameters. That's 3 variances, 3 covariances. So if I have wave as 1, 2, 3, and I let it be unstructured, can that possibly be wrong? Teresa, what do you think? Can that unstructured be wrong? Ugh. Not within. The only way it could be wrong is if each group needs a different unstructured matrix. It could be wrong in heterogeneity of variance with respect to group, but what about with respect to time? No. Unstructured is the answer key. It is as many parameters as there are to be estimated. It's a description of the data with respect to the variance and covariance over time. It can't be wrong. If it estimates, have that. There's not a whole lot of people in each of these groups in this study, so I wouldn't try to go heterogeneity of variance, but one could, I suppose. So that's pretty easy, and that's why I didn't put e's and u's in my equation, is because it would be easier in the text to just describe we allowed an unstructured model for the variance in which each variance and covariance across time is estimated separately. That sentence is going to be more easy to understand than some kind of complex notation to indicate different e's and different u's and so forth. In terms of the fixed effects of time, I have these coded so that I can represent differences over time in the way that the study has aligned itself. So I have it as a piecewise model. So I'm setting it up so that wave 1 is my intercept. If wave equals 1, then each of my 2 slopes is 0. So I've defined the intercept that way. It's the point at which all piecewise slopes are 0. If wave is 2, the first slope kicks in, but the second slope does not. And if wave equals 3, then the first slope shuts off where it left off, and the second slope kicks in. So the model then gives me the intercept as the predicted value at wave 1. It gives me the difference between wave 1 and 2, and then it gives me the difference between wave 2 and 3. So I have 3 fixed effects: a fixed intercept, a fixed slope 1, and a fixed slope 2. Can that be wrong with respect to time? How many occasions do I have? 3. If I fit a fixed intercept, a fixed slope 1, and a fixed slope 2 to my 3 occasions, how many fingers am I holding up? 3. How many occasions do I have? 3. Can this be wrong? No, just identified. Andrew, you're staring at me like, huh? Yeah. I hear you. It's that sleep deprivation, isn't it? It's harsh. Yes. I'll give you a pass. You can take a nap in the back if you need to. I understand. Been there. No, 3 means time 1, time 2, time 3. Rather than letting them just be saturated, I have described them in a way that allows us to test hypotheses with model parameters. I could have just fit the saturated means model. That would have been another thing. That would have phrased it in terms of dummy codes for mean differences across time. That would be equivalent. So this is an instance in which the data don't have a lot of complexity to them. There's 3 means, there's 3 variances and 3 covariances, and I'm just going to let them be whatever they need to be, and then look at how group is different. So I have wave 1 intercept. If these groups were actually randomly assigned, should I have a group effect at wave 1? Hopefully not, right? If treatment worked, should I have a group effect at wave 2? Yes. Now this one is tricky. It looks like from my picture that I don't have a group effect at wave 3, but that would only be true if 2 different things happened or some combination thereof. The waitlist control got better and the original treatment maintained. So there's 2 different factors there that would be of interest in looking at group differences. So I've written out what the code would look like to get all possible comparisons of interest. So I have the treatment effect at wave 1. So again, the thing I'm going for here is treatment effect, group difference. So that gets the 1. If I'm talking about the group difference at wave 1, then that's when my 2 slopes are set to 0. So I really don't need that at all. I could just do this instead. But for the sake of pedagogy, I put them in there. Treatment effect at wave 2, still treatment 1 because that's the thing I'm trying to estimate. And the values here reflect the codes for slope when wave equals 2. So slope 1 gets a 1, slope 2 gets a 0. And then at wave 3, all 3 of the terms get a 1. So now the question, did treatment work? That's a fairly straightforward question, right? But how do I answer that given the way they set this up? Well, did treatment work for the first group? Did it work for the second group? Did it work equally between groups? There's 3 possibilities there. So here's the first question. Let me put it this way. Did the waitlist group improve? Now, they shouldn't have, right? This is my control group. So if they do treatment as usual, right, maybe they do improve to some extent. The question will be, did they improve more after whatever special treatment I gave them? So this estimate statement allows me to address what would have happened if I just let them be. That's my waitlist control group from wave 1 to 2. Slope 2 for the waitlist control group then is the fixed effect of slope 2 given by the model. So if my control group is the reference, the fixed effect of slope 2, its simple main effect, is for the reference, which is the waitlist group. So here's one of my treatment effects right here. Here's the other one. Slope 1 for the treatment group. The model doesn't give that to me directly. It gives me the difference between the slopes. So to get what it would be for the treatment group, the group coded 1, I have to add slope 1, which is what it is for the waitlist group, plus the difference in slope 1 for the treatment group to get to what it is for the treatment group. So there's two ways to look at this, I would say, and a complete report I think should include all of them. This right here tells me, did the treatment group change? But in order to know if they changed more than they would have had we left them alone, that's the interaction term. So as time goes on, they may have improved anyway. That is going to be proxied by the slope for the weight group. Did they improve more than they would have is the interaction term between treatment and slope 1. Andrew. Yes. So let me write it out the long way. That might be a little more intuitive. So the bar, that allows us to ask for main effects and interactions in one shot. So if I go like this, slope 1 times treatment, slope 2 by itself, and slope 2 times treatment. That's what it looks like. So I'm saying that when treatment is 1, we're talking about the treated group as opposed to the weightless control. Weightless control is the 0. So let me walk back through this in the logic of interactions. This is a good review. So slope 1 would have been, if treatment wasn't in the model, the change between wave 1 and wave 2. Because treatment is in the model as an interaction, oh wait, hang on, I forgot my main effect. There we go. So here's main effect of treatment. Treatment interacts with each of the slopes. That means the main effect of treatment is specifically when each of the slopes is 0, which is at the beginning of the study. So that main effect of treatment is going to give me the group difference at the beginning, which should be none if random assignment worked. Now we look at these two terms here, slope 1 and slope 1 by treatment. Slope 1 represents the change between wave 1 and wave 2. And because it interacts with treatment, it's the change between wave 1 and wave 2, specifically when treatment is 0, which is the control group. So slope 1 right here is the business as usual change between wave 1 and wave 2. That means that slope 1 by treatment is how the treatment group changed more during the first interval. And I would say that is the definition of the treatment effect, because you have to show that they grew more than they would have. And that's the whole reason to have a control group. Otherwise, you don't know why they grew, because hopefully if they were in the hospital, they should be getting better anyway, right? Other than whatever special extra thing you're doing for them. Analogously, slope 2 is the change between wave 2 and wave 3. Because slope 2 interacts with treatment, the main effect of slope 2 is its simple effect specifically when treatment is 0, which is control. So slope 2's main effect then is the treatment effect in the weightless group. That's before and after for them. Slope 2 by treatment is then how the change between wave 2 and wave 3 differed in the other group. But it differed for a couple different reasons, and so that parameter in and of itself is maybe not as interesting or informative. It differed because they were in a different group and because they were no longer being treated. It was a follow-up test. So we have this interesting case where the things that we want to know are kind of buried in here in some respects. So this is a case in which estimate statements really are needed to tease out exactly what you want to know. Does that help?
That does help. I think I was really just getting lost in how that's like where you rewrote the model statement, or like the syntax of how it leads to that.
Okay. Well, if you don't like this, then don't use it. It's helpful once you get into really complex models and you don't want to have to keep track of all the things that should be underneath it. Or else if you're like doing your due diligence just to make sure there isn't a 5-way interaction, right? You can just @5 it and check it and not have to write them all out. But yeah, it's less intuitive, I think, to write it that way. Okay. So here's then what we have. Slope 1 for the weight group, that should be 0. Slope 2 for the weight group, that should be a positive number. Slope 1 for the treat group should also be a positive number, and slope 2 for the treat group should be a 0 again. So we want some of these slopes to be positive and some of them to be negative in accordance with our hypotheses. But this would allow us to figure out, did the groups change during each interval? Did they change differently? And then the last one is a little tricky, but if you wanted to know if there was any difference between the groups in the effectiveness of the treatment. Because if you're using, say, the same people to implement this process, do you think they might get better at it if they've done it a few times? Does practice generally help most things in life? I think so. So you could investigate that as the difference in the treatment slope, the acute change before and after, across your 2 runs of this program. So we know already here slope 2 for the weight group is when they should grow, right? The weight group grows on slope 2, which is, where's my picture? This one. Let's go back to the picture, that makes it easier. I want to know if the green line and the red line are parallel. How's that? That's what I want to know. In terms of the model, this red line, because this is the reference group, is given directly by slope 2. This green line is given by the sum of slope 1 plus the interaction of slope 1 by treatment. Are you with me? I'll say it again. So what I want to know, are these 2 growth lines parallel? This red line right here for the reference group is given directly by the simple main effect of slope 2. This green line for the treatment group is given by slope 1 plus treatment by slope 1 interaction. So if I know what made the red line and I know what made the green line, I just have to subtract one from the other. And that gives me the difference in those 2 slopes. And that's how I came up with this line right here, where slope 2 is the red line, slope 1 plus the interaction of slope 1 by treatment is the green line. I'm contrasting one and the other. Yes?
So, can you speak about how the red line is determined by the slope 2,
Mm-hmm.
and then the green line is determined by slope 1 and the interaction with slope 2?
Interaction with treatment.
Not with slope 2.
With treatment, yeah.
Okay. So then the red line, why would the red line not also be slope 2 in interaction?
It would, except the interaction term zeroes out, because that is the red line specifically when treatment equals 0. Whereas for the green line, that's when treatment equals 1.
Well, when treatment equals 1 for the second part of the red, because they did the treatment at 2?
Treatment is my time invariant predictor of red versus green.
Okay.
So think treatment is maybe not the best label, it's group. No? So, yeah, see, it's not just random linear, right? It's tricky. Don't make me bust out Run DMC again. No one wants to hear me rap. So here's, let me see. This is what makes the slope of the red line right here. Slope 2, and then it would include the interaction as well, except that this is when the red versus green variable is 0, because it's red.
So it's sort of like a binary. What group it is?
Yep. Yeah, rather than thinking of it as time varying treatment, I'm thinking of it as which group you're in, and each group is in treatment during part of the time.
So in theory, could you have done it the opposite way, where the second group is, so like the green group would just be, slope 1, and the red would be slope 2 of interaction? And just flip it?
Yeah, I could switch whether the reference is green or red, yeah. Or I could do something entirely different. So I get the sense that this is making your guys' head hurt. Is that an accurate reflection? No one's willing to admit it. It made mine hurt to figure it out. Scott, are you willing to admit it? Yeah. Is a little bit? Yeah. So there's other ways to play this game. Let me give you an alternative setup here. So this is confusing, potentially. What if I did something like this? I'm going to use red v green. You are allowed to write your model in any way that makes sense to you and gives you the answers that you want. There are lots of equivalent ways to write it. So here I am making use of a couple new variables. So red versus green is my code for which group we're talking about. Okay, who got treated first? Red is a dummy code that is equal to 1 if you're in the red group and 0 if you're in the green group. Green is the opposite. It's a dummy code that's equal to 1 if you're in the green group and 0 if you're red. So rather than casting the model in terms of group differences, I've decided to cast it in terms of what happened to each group specifically. So this is still the difference in groups at the intercept. This is slope 1 for the red group. This is slope 1 for the green group. This is slope 2 for the red group. And this is slope 2 for the green group. The end. Is that easier? Is it the same thing? Here, let me add in parentheses here, intercept, because that's in there as a fixed effect even if we don't write it. How many terms are in this model for the means? Not a trick. 6. How many means do we have to predict? 6. How about up here? The way that we did it before. How many terms are in this model for the means? 6. You can set it up however you want. It's 6. You're allowing all 6 separate means. The only difference is what spits out by default in terms of a test and what you actually have to ask for. So I actually like this way better because it gives you more directly. Did the red group change during slope 1? They shouldn't have. Did the green group change? They should have. Did the red group change? They should have. Did the green group change? They shouldn't have. And then if I wanted to know if the red or the green group changed more than they would have if they had been left alone, that's the difference in the first 2 slopes right here. And if I want to know if the treatment program got better over time, if the lines were parallel, that's going to be green slope 1 versus red slope 2. So there's nothing that says that when you have groups that you have to phrase everything in terms of group differences. You can phrase them as group-specific effects, and the term for this, by the way, is a nested effect. You can think of these dummy codes as switches that allow the fixed effects to turn on and off for different kinds of people. This can be easier to work with sometimes in certain kinds of designs. These types of switches are also helpful if you ever have this type of design that has an empty cell, like a control group that doesn't really correspond to the full crossing. You can set it up this way to get all of the predicted means. So, does that help at all? Maybe? Okay, now potentially trick question. These are all fixed slopes, right? Do I need to test for random slope 1 and slope 2? And I'll phrase that more obviously. Do I need to test for random slope 1 and slope 2? No, why not? What kind of variance model did I say I was going to stick with at the very beginning of this story? Unstructured. The whole point of including random effects would be to try to create something that is as good as unstructured. It'd be redundant. Unstructured is already allowing the variances and covariances to differ over time as they need to. That's what the random slopes would have done. Further, how many random slopes can I have with a 3-occasion design? Can I have both be random at the same time? Nope. I could have only had one. So odds are good, that model would have fit worse than unstructured anyway. So this is an instance, it's perhaps a semantic distinction, but I probably wouldn't call this a multi-level model or a mixed model. I would call it a multivariate model. The way I'm looking at this problem, each occasion is like a separate DV, and I'm just letting the DVs be correlated. If I were to draw this as a path model, I would have a box for the time 1 outcome, wave 1, a box for the time 2 outcome, a box for the time 3 outcome, and I would have my box for group predicting each one, and I would have residual covariances among the boxes for time. So that's a path model that is the same thing as what you're looking at up here. You would have to ask for contrasts between the paths to get all of the pieces of information that you want, though, the same way that we have to ask for estimate statements or trick out the model for the means. However, why might I not do this as a path model? Can you think of a reason we talked about last time that has to do with estimation? I heard you. What was it, Amy? So long as I'm in some kind of likelihood, I wouldn't drop people. That's why I wouldn't do it as an ANOVA with least squares, even though it's a multivariate ANOVA model. But what flavor of likelihood? I need REML with few people, right? Do path models offer REML? Nope. So that's why. You can talk about it as a path model if you wanted. You could make a picture if you wanted. But at the end of the day, it's a multivariate model with REML, however you want to talk about it. One thing I've gotten in the habit of doing in my papers now that nowadays supplemental material is readily available, I hand out syntax. I hand out whatever syntax I used for the models and I stick it in some kind of appendix and I stick it on my website. That way if there's any question as to what I did, they can download it and see. And it helps people cite you more because they say, following this person, right, I stole your syntax and used it in my study. So it makes it, in addition to being transparent and reproducible, citable. So that's always nice. And if you can make your syntax in more than one program, even better. All right. Any questions on this little story here? You want the next one? So this is a more recent story. This is a real world problem that was given to me. So this is real data. I have taken off most of the identifying information though, so we can just talk about the story. But there was a county in a state where there was a whole bunch of pollution discovered, and it was initially publicized that there was this pollution and that people were going to do things about it, and every house in this area got tested, and some of them, the pollution was over some arbitrary line where they decided they needed to remediate it, so they did a bunch of stuff to clean it up for some of the houses and not for others. And there is a lawsuit being brought about by the people whose houses got fixed, that the process of fixing the house has hurt their property values. The fact that it was broken and isn't anymore, people apparently viewed as a bad thing. Even though all the houses were broken, just some of them were more broken than others. So it's actually a backwards argument than you would think. That I would think not fixing it might be a problem, but it was the people whose houses got fixed that thought that this process had harmed their property values. So this is a very different situation than research where like there's a lawsuit, right? Like this person could be brought in to testify with this data. Did it look like this process harmed property values? Well, okay, how do you answer that question? And how do you make sure that your answer would hold up in a court of law? So they have 18 years of home value data, and here is what it looks like. So home values tend to increase over time, with the exception of like 2008 or so when everything tanked and now it's all coming back again. And sure enough, it looks like the houses that were not treated cost more, so have better property values than the houses that were treated. However, Mother Nature did not randomly assign pollution to these houses. So we have to think about not only modeling what is it that causes changes in property values over time accurately, but also what is it that causes some houses to cost more than others. So in particular, this person had two events that they were concerned about, indicated by the blue lines on this graph, where the first one, this is the point at which the fact that there was pollution became more well known, and it was publicized and there were meetings and newspaper articles and stuff like that. And this is the point at which the cleanup started. So they wanted to know whether or not there were differences in property values before and after these salient events, and if there were different differences as a function of whether or not the house got remediated. So we'll put in this graph here. Do I throw in my random linear model and call it done? Well, some of it looks linear. But this is another instance of our friend piecewise models, I think. And piecewise phrased in a different way than what we had gotten practice with last semester. Rather than wanting to know what is the rate of change during each of these time periods, we want to know, is there differential change between time periods? So there's 18 years of data that's relatively complete. This is the model then that I helped this person start to set up. This is based on chapter 6, where I'm using the terminology jump and slope, where slope is change over time and jump is a potential acute difference in the intercept. So there are 3 slopes and 2 jumps given these 3 different phases of time. So here's what the code looked like then to try and mimic that process. So we have one continuous slope here that operates through all of time, centered such that the intercept is the first occasion here, so you're -1. So that's my random linear, potentially. That's my linear slope. Then we have, if it's before year 6, which is when the meeting started, all of the variables stay 0. If it's after year 6, we pick up this, which is a dummy code. It turns on after the year 6 point. And then we pick up slope 2, which is the current year minus 6. So this slope 2 is tracking how many years it's been since 6. How many years has it been since this pollution was publicized? Then we have when the cleanup started. So if it's less than 14, the third phase variables are shut off. If it's greater than 14, we pick up a potential intercept shift, as well as how many years it's been since 14, slope 3. And I also put in, I created this here as just a simpler indicator as to which phase we were in, whether it was the first phase, the second phase, or the third phase, because I thought that might be useful. So in terms of the model, here's all of the stuff put together. Slope 1, jump 2, slope 2, jump 3, slope 3, each of which is interacting with treatment, which in this case is whether the house was remediated, whether it was treated. So you can guess what happened probably staring at the pictures. Does it look like there's any need for a jump? Not at 6. That looks pretty darn continuous to me. After 14, there's an abrupt change, maybe. From 1 to 6, that looks a little bendy, but mostly linear. From 6 to 14, does that look linear to you? No, that's a bendy, but not quite a quadratic bendy. So this is an instance in which, like, if I were testifying in a court of law, I would throw as many tricks at that middle section as possible to try and get the right fit for time. I would make that fit before I made any kind of conclusions. How about from 14 to 18? That looks fairly linear. So our goal then would be to try and figure out what the model for the means needs to look like to capture those shapes. And the shapes are largely the same between these two, just if you plot, these are the saturated means for each of the types of houses. Now on the random side, this is a fairly big sample of houses. However, the unstructured matrix would not converge. That would be an 18 by 18 matrix of variances and covariances. That wouldn't converge. So here's an alternative, simpler model for the variance. When I have this combination here, what is that? Looking for either vocabulary terminology or what does it predict? I'll take any of those. This is variance components, which means what? You remember? Nope, that's okay. There's a two-word phrase that describes the two of these together. Random intercept only, or U plus E, or this is compound symmetry. So this says that houses differ from each other only in how much they cost at the beginning, and that's it. That's pretty unlikely. The random effect structure, though, in this case is very tricky because of what each of these slopes represents. So we could throw in slope 1 here. That would be a fine thing to test, and I do believe that was significant in the data. And what that means, if you look at just these two terms right here, that allows houses to differ from one another in how much more they cost over time. Basically the rate of increase in their property values. Some houses grow more in value over time. That seems plausible, right? if I throw in slope 2 here, the model actually doesn't converge. Now, in contrast to what slope 2 meant before, this slope 2 means something different. So before, the way we had set up the model was direct. This is slope 1, this is slope 2, the end, right? This slope 2 is phrased as an increment. So note that slope 1 never shuts off. Slope 1 runs the whole way through the data as a linear slope. So what slope 2 does is to describe the difference in the slope after year 6. Are there individual house differences in how property values changed after the pollution was publicized? And in this case, there was no evidence of that. Likewise, one can test slope 3, which is, are there individual differences in how the increase in property values per year changed after year 14? Slope 3 is also phrased as an increment. It's an increment beyond the change after 6, and it's an increment beyond the slope that's operating through all of the phases. So it is, if a random effect of slope 3 would be individual house differences and how the rate of property values changed per year differently after year 14. Individual differences in the shift of the slope. And there was no evidence of that either, I believe. The model wouldn't converge. So this is what one might be left with. So my question down there then, is this likely to be sufficient? We don't know because there is no answer key. We don't know in terms of being able to test -2 log likelihood differences because there's no 18 by 18 answer key matrix to come back to. Now we could do descriptive things. We could just print what the variance is at each occasion and see how well the model captures it. Same thing with the covariances between there. I mean, we could sort of backwards engineer our way into some sort of fit. But this specification here of continuous time doesn't really match what is thought to be going on in terms of what caused change in here. So here's another possibility that one could have using these phase variables. One could do something like this. This isn't something you've seen in any of my examples, I think. I'm capturing this phase, which phase you're in, like it's a multivariate outcome. When I say random phase type equals UN, phase is up on the class statement, which means that SAS understands that it's a categorical variable. So what that would get me is a 3 by 3 set of random intercepts, one for each phase. So that would allow the variance to change across these 3 phases of the study, a variance across houses, and it would allow an imperfect correlation between them. So if you think about the difference in what it would mean if you had, let's say, this versus this. That versus that. It's kind of like a factor model, where random intercept would be one factor. Random phase would be 3 factors. So random phase would allow a non-perfect correlation between the intercepts in each section of the data, and potentially different variances as well. So that's a different way of thinking about heterogeneity of variance and covariance that corresponds to the design of the study a little bit better, even though it's not directly implemented within the model for the means. That's one thing one could do. Beyond that, we have an 18-year set of data. Do you think it's likely that house prices are more related from one adjacent year than far apart in time? Yeah, I think that's pretty reasonable. How much you pay in 2009 is related to how much you pay in 2010, even beyond the fact that some houses are more expensive. Does this R matrix here capture that idea? Type equals VC? No? Could it? Sure. What could I throw in here also? Sure, I could do autoregressive. That would say years 1 year apart are correlated R, 2 years apart are R square, and these are the residuals after controlling for whatever intercept differences. Topolit's reduced form also could work for something like this. So this is an instance in which I would probably try different things, look at what the prediction is, try to get as close to the descriptive data as possible to pick something. And that's just the time part. So if I am being sued because I fixed houses and ruined property values, what's my counter argument here? How do I get out of paying these people? I don't want treatment differences. I want the null. They started out lower before I did anything, right? Now, how many of you own houses? Good, that's the right answer. Do not own houses as graduate students. How many of you would like to own a house at some point? Yes. What makes houses cost more? Some houses cost more than others within the same vicinity. This is not a trick. Square footage, number of bedrooms, number of bathrooms, size of the lot, how old it is, how new the kitchen is, et cetera, right? There's a million things that one would have to control for, given that these houses were not randomly assigned to being treated. Perhaps the treated houses were just shittier to begin with. That's entirely possible. And as Aaron said, look, they cost less before any of this got started. So these, even without doing any models, if I were a jury, I would be fairly well compelled by these parallel lines here. Green is lower. It was lower, it stayed lower. You would have to throw in all kinds of covariates, but if you're talking about how property values change over time, then this doesn't seem to indicate that they have a case. But there's other ways of operationalizing harm to property values. So whenever we go on vacation and like Florida or someplace, one of the things we like to amuse ourselves is look on Zillow, like wherever we're staying, to see how much like it would cost to buy it. You ever do this? Yeah, it's like, no. It's like when you're in someone's Airbnb, you're like, this is great, I need one of these. Like, how much would it cost? And so you go on Zillow and drive around and start looking at things. And they always have a statistic that amuses me because it's price per square foot. And if you look at this for like a house around here, it's like between $100 and maybe $150 per square foot. Like the ones like on the beach in Florida are like $700 a square foot. It's insane. Like it's this huge difference. But that's another metric besides just changes over time. One could argue that you don't get as much more for the size of your house in the green houses versus the red houses. So you could model how the ratio, for instance, of size price per square foot changes over time, and whether there are sections of the data in terms of what happened that caused that to change differently. So I think that this is one of those cases where I could do analyses for like 6 months and probably still not feel like I've got it right, like if it's for a court of law. But the point of the example, though, is that throwing a random linear model at this would absolutely be not adequate. That's the point of the story. And even the piecewise model is not adequate unless one finds a way to model the nonlinearity within each of the pieces and the differences between pieces as well. Okay. Yeah. Questions or thoughts about that? No. Do you want another quick story? Just off the top of my head? Paper that's currently under review, actually. A researcher at Juniper Gardens, Kathy Tiemann, and I are working on a paper where she has this long-term intervention in kids with autism, helping them to become, I guess, more peer-friendly, maybe. I don't know quite the right words, but it involves an iPad and it involves peer-to-peer training and whatnot. And she has a fairly complicated longitudinal design where she watched both the control kids and the treatment kids, which were randomly assigned. She watched them like a couple times a week for several weeks in a baseline period. Then there was a treatment period where they taught them how to use the app, or they taught them, whatever they would do, treatment as usual kinds of things. And then there was a generalization period where they talked to another friend that they hadn't talked to before. And then there was another generalization period where they talked to a brand new person. And then there was a maintenance period. So this happened during an entire school year, and it was a 5-phase design where something different happened during each phase. But within each phase, there were somewhere between like 3 and 40 observations. Yeah. And we want to know, did treatment work? And did it keep working, right? Because maintenance is the big one. Doesn't count if they go back to their old ways. Right, clinicians? That's what treatment means, right? See, I'm a psychologist today. Child linguist last time. Child linguist? Languager? I don't know, something. So what do we do with that? So I'll write this down here, 5 phases. Somewhere between like 3 and 40 observations within a phase, which is all unbalanced because these are real kids in a real school and they got to be assessed whenever they could, right? What do I do with this? Nobody knows. Well, phases should trigger something in your heads, right? What does that trigger? Something piecewise, right? But how do we deal with the fact that there's multiple observations within each piece? This is an instance in which I would either go 3 levels or multivariate. So 3-level models we're going to talk about. But the idea of a 3-level model, let me steal some code here. So we'll call this outcome. Let's go to an empty model here. This is foreshadowing. And there's not going to be a repeated because the data are so unbalanced that there's no hope of any kind of answer key. So I'll do repeated sort of as a placeholder down here so you can think about it. So here's our classic empty model. This time has 3 levels instead of 2. So the purpose of a random intercept does 2 things, right? It distinguishes between from within variance, in this case between from within child, and it also induces a correlation of occasions from the same child. Well, we still need that. So this first random intercept then does that role. It distinguishes what is mean differences between children and how much they talk or whatever this outcome is from variation within a child across the time. But that would assume that all of the observations within a child are equally correlated regardless of how far apart in time they are and regardless of which phase they're in. That seems unlikely. So we bring in the second random intercept, which turns this into a 3-level model, where the subject then is defined as the unique combination of kid and intervention phase, of which there are 5. This random intercept then does the same type of thing. It allows mean differences within kids due to which phase they're in. So not all phases are the same. And in doing so, it allows a different correlation of observations that come from the same phase than observations that come from different phases, still within the same kid. So this same type of setup is useful whenever there are potentially multiple levels of time, layers of time. So for instance, I talk a lot about like fluctuation studies where there's multiple observations within a day and multiple days. The setup for something like that would be there, where we would have one random intercept that allows mean differences between people, and another random intercept potentially at the day level that allows mean differences between days within a person, and at the same time allows occasions from the same day to be more correlated than occasions from different days, still within the same person. So there's 3 kinds, potentially, of variance here. Here's between people. This is going to be either between days or within people. You can think of it either way. And the repeated that's down here, the residual that's left, is within day. Can you guess how I might decide if I need a 2-level model or a 3-level model? Basically, whether or not this highlighted line is necessary. ICC would give me an effect size. Can you think of how I might get a significance test, whether I need that extra thing in my model for the variance? Andrew? That's a nested model likelihood ratio test, yep. Same as always. Yep. So back to the data story here. In terms of organizing the data, I had to create a new variable for time relative to not what was going on in the school year, but where each observation was relative to its phase. So I had to get the date at which each phase began for each kid, because it was a different date for each kid, and then calculate, given the date of the observation, how far into the phase each observation was. So each phase essentially started over with a new time 0. So my model for the means looked like this in the unconditional model. Here's another trick to make it easier to work with. I took out the intercept. Like, you can do that? You can. Because without the intercept, this phase variable, it became like I dummy coded it. So what I get then is what is the predicted intercept at the beginning of each phase. I get one for phase 1, 2, 3, 4, 5. I also get what is the predicted slope in each phase. So I can find out if each phase has a slope, and I can also test quadratics, for instance. During each phase, if there's some kind of nonlinear change, I can do like this. Actually, probably be easier to understand if I keep it like this. Like that. That gives me linear and quadratic slopes per phase. If I want to know if the slopes are different across phase, that's estimate statements. And if I want to know if the control group changed differently than the treatment group, I throw a group on there. And a whole lot of estimate statements later, I have my answer. In terms of the model for the variance, what I ended up doing, because all of the random slopes fell apart for the most part, is doing that again. Took that out, switched it back to multivariate. Random phase. Essentially, I gave each kid 5 intercepts, and I estimated the correlation between them. I gave them 1 intercept for each phase. So it was like I had 5 DVs, and I fit a random intercept for each one, a separate random intercept variance, and a covariance among them. And then the residual then, I'm assuming equal residual variance across phase if I leave it like that, but you can also do group equals phase to allow different residual variance within each phase, because they may be more alike during baseline periods than during treatment periods or something like that. And that's what it ended up being. So I'm happy to share SAS code with you if any of you would like to see more in detail. But this is the kind of thing that once you start learning these twists of levels and multivariate, that you can address more complex data when you have multiple levels of time potentially. Make it multivariate this way or stack it up. So that's where we're headed later in the semester. I'll have more stories then. Okay. Any questions? Are we done? I think we're done. Done a whole minute early, I think even. Wow. So office hours start now. I will see you Wednesday.